Greetings, welcome to yet another video on smart technology. In this video we will discuss Foundation Fieldbus technology. This slide shows the famous automation pyramid. Field level is level 1, where we find digital networks, especially the Fieldbus. Level 2 includes controllers, SDCDs, PLCs, and PCs, CNC tech. Thus, the Foundation Fieldbus system exists as an intermediate component positioned between Level 1 and Level 2. Level 3 encompasses supervision systems, HMIs, workstations, as well as PCs and computer terminals. At Level 4, we have plant management, all of the plant management. Level 5 is categorized as corporate status. This presents the technological landscape crucial for grasping current technologies. On the bit level, there are the so-called sensor buses, which are simpler networks on and off. Examples include ASI, Interplus, and Seriplex. Then come byte-level networks, a bit more complex, known as device buses. We have Interbus S, CAM, Lawnworks, Modbus, DeviceNet, and Profibus DP, one of the most recognized, together with Modbus and DeviceNet. Next are more complex networks at the level of PID control, which transmits a greater quantity of information. Here we have the Quattro Avinte heart itself, the Aries heart, the Profibus PA, which is specifically designed for transmitters and field devices, and the Foundation Fieldbus as well. Therefore, here we present all of the current technologies in the market. The Foundation Fieldbus technology is a digital protocol that offers a digital communication as well of a two-way communication. That is to say, we transmit and receive information from the field devices, and they communicate with one another as multi-point. We have the communication between these field devices totaling 53 characters, factory ground, with automatic oversight for monitoring and control. Therefore, in essence, the Foundation Fieldbus serves as a local area network designed for field devices, for communication with the control system. In conventional setups, conventional DCS solutions, each field device supplies 4 to 20 kHz MA current to I/O cards, maintaining the essential information while meeting the character limit requirement. They exclusively transmit this information and do not receive any data from the DCS system. The DCS, for its part, transmits the information to the computers and the supervisory management systems. The traditional system is based on this process, working similarly. Once the control strategy is set, the signal sent to the positioner or valve is in the range of 4 to 20 milliamps, which ensures effective transmission to actuate the valve. In the Foundation Fieldbus system, there's a single channel. This channel goes out from the CPU or from a Foundation Fieldbus scanner connecting field devices on a network using a single pair of wires. This distinguishes the physical setup. We refer to this channel in Fieldbus as the HI network. The controller will communicate via Ethernet with the switch, and consequently with the computers for management and engineering configuration. This is the main advantage of the Foundation Fieldbus network. It no longer sends the analog current signal of 4 to 20 milliamps. It transmits a completely digital signal. Each of these channels has the capacity to handle a maximum of 16 devices, ensuring efficiency. This is a significant advantage for saving on cable costs, installation savings, and design simplicity. Therefore, in a system using 4 to 20 milliamps, to summarize, all devices utilize a single set of wires to function properly, sending this analog signal in a single direction to the I/O cards that are located with the controller and the management, engineering, or maintenance computer. Once again, when assessing Foundation Fieldbus systems for comparison, there is a completely digital signal that transmits and receives. This is a key differentiator through one channel with a pair of cables, supporting up to 16 devices. These are the big differences, one of the important differences. It also saves costs when intrinsic safety is required. In a conventional setup, every device encounters an individual barrier, representing a total of 73 barriers. In the Foundation Fieldbus system, we use a single obstacle blocks multiple devices, moderately preserving meaning. Another important differentiator is that in a traditional network, in a standard system, all control strategy blocks are consolidated in the controller's centralized location. Refine the text for a Fieldbus system. We can consolidate and combine as well in the controller. Another significant differentiator is distributing the control strategy, the blocks to the field devices. Another key piece of information, in a hard system with 4 to 20, if we operate with 4 to 20, utilizing hard digital communication, the speed of hard is 1.2 kilobits per second. In the Foundation Fieldbus network, it will be about 30 times higher, 31.25 kilobits per second. Each Foundation Fieldbus channel measures 1,900 meters. By using a Foundation Fieldbus repeater, the DF48, we can repeat the distance up to 4 times. This makes it possible for us to span a distance of 9,500 meters. In terms of intrinsic safety, we can have a safety barrier for each channel. If the DF48 CPU has 4 channels, we can implement 4 barriers. The distance can reach 1,000 meters per segment. A major benefit of the Foundation Fieldbus network, the control strategy can be applied in multiple ways while maintaining flexibility. Thus, in one control, we can implement the PID in the CPU and divide it among the field devices. And we can also, in our strategy, make sure to utilize all the blocks in the field devices, whether or not you have a PID. It depends on your design as well as your specific requirements. Thus, there is significant flexibility for developing the control strategy. In a Foundation Fieldbus network, we gain an extended perspective. Our field equipment gives us a broad perspective. This text contains 74 characters. Since it is a digital system that sends a series of information, including status, and is bidirectional, we can see our field equipment more clearly. This helps us understand the equipment better. In a standard setup, we receive a mere 4 to 20 milliamperes, which is the conventional range. Thus, we are limited to the information from the field equipment. For maintenance, the Foundation Fieldbus network is quite interesting because it sends us the fault. Furthermore, it provides information on the position of the fault, such as a malfunctioning sensor. In a standard system, 4 to 20 milliamperes, the transmitter transmits a current signal to the controller. For instance, milliamperes convert to 15.3 mA. In a Foundation Fieldbus system, it will send and receive important information from the transmitter. It will receive the tag, its name, the value, the unit, the status, and if an alarm exists, it will also convey the alarm. So, see the great advantage of having a fully digital system. Therefore, with status information, we enhance management data. We greatly expand what is highlighted in red, which represents management information. What is in gray are control information, which also shows an increase. So, the amount of information we receive from a digital network, Foundation Fieldbus, is extensive. Being a completely digital system, we have, as previously discussed, various savings. Regarding installation, when compared to a standard system, our installation is more efficient. In a conventional system, multiple input and output cards are needed, which results in a lengthier process, including protection. And in a Fieldbus system, we can create a much more efficient configuration with significant savings. In the traditional system, to establish communication between devices and between the devices and the supervisory system, sometimes we need a series of drives. Using the Foundation Fieldbus system, we collaborate using a regular interface for communication purposes, employing OPC to connect with the supervisory system, making it much easier, the system's digitization. To incorporate field equipment into this new technology, we utilize a technology known as DDL, Device Description Language, where we place this DDL into the computer in the software you are using. The big advantage is that the configuration software is universal, fitting any manufacturer, integrating field manufacturers via DDL. Thus, via DDL and 3 files, we can incorporate new equipment into the configuration software. It's a great convenience. The Foundation Fieldbus protocol didn't reinvent the wheel. It didn't come from nothing. It adopted the ISO OSI model, which includes these 7 layers we see here. From these 7 layers, some layers were removed, and thus it was developed into the Foundation Fieldbus communication model. The user interface was retained, the communication stack, and the physical layer was developed. Therefore, in the physical layer, we have the following characteristics. In HI, we find a field network, referred to as low speed, which will substitute the 4 to 20 milliamp technology. Operating at a speed of 31.25 kbps, the bit rate is relatively moderate, maintaining efficiency, directly provided by the bus itself. There is an option for built-in safety and a distance of up to 1,900 meters without needing a repeater. Keep in mind that we can use repeaters. Adding a repeater extends the range by another 1,900 meters. We have the option of incorporating up to 4 repeaters into a Foundation Fieldbus network. The network linking the PLC and the controller, and between the controllers and the computer, it's a high-speed Ethernet network of high speed, where we achieve 100 megabits per second. This network can use Ethernet or fiber optics as its physical medium. In the future, we might reach 1 gigabit per second. Thus, in a standard installation, we will see the field channel, known as HI, operating at 31.25 kilobits per second. This information is sent to our CPU, controller, and bridge as part of the process, where we will also have high-speed Ethernet communication at 100 megabits per second, connecting controllers and computers. Okay? Therefore, in an HI network, we have a speed of 31.25. Here we find the typical installation, where we have the power source that will supply our field equipment. At the start and finish of our network, we have the initial and final terminators, BT302, which is here, where there is a capacitor and a resistor. Okay? If we measure the signal voltage, we will have a peak-to-peak voltage of 0.75 to 1 volt, peak-to-peak. This is the typical signal. This is the current being used. It contains a total of 42 characters, from 15 to 20 milliamps peak-to-peak. And a voltage of 0.75 to 1 volt peak to peak. This capacitor has a value of 1 microfarad, and the resistor is 100 ohms. Connecting an oscilloscope to the network, we will see this voltage of 750 millivolts, peak to 1 volt. Preferably, we will observe a square wave with the shape of a square, with a frequency of 31.25 kilohertz. A Foundation Fieldbus network status is composed of the good status, normal condition. Bad indicates a failure state. Uncertain signifies that the signal exceeds the set range, for example, going beyond the programmed parameters. Therefore, we should observe the statuses between the blocks, between the devices, and check their substates as well. There are various substates. The system will automatically take a safety measure if there is a failure, ensuring optimal security. For instance, a sensor failure initiates a safety action. Ensure the valve is safely positioned, for example, making it enter a secure state. To ensure safety, the PID block requires the PID controller to enter into a secure state. For us, this guarantees a secure transfer and a seamless initialization, ensuring a smooth process overall. With the use of statuses, we have the ability to work with maintenance, proactive, hence schedule maintenance according to equipment diagnostics to maximize efficiency. Scheduling calibration by utilizing saved equipment calibration data in order to maintain accuracy and precision. In the history, calibrating and maintaining various instruments together with fewer interruptions. Maintenance and calibration done during planned downtimes rather than during emergency stops. So, in an automation system in a factory, it's best to plan the downtime. Don't pursue faults during stops. This is vital. Increasing the plant's availability, and also without wasting time on unnecessary maintenance. Through the statuses, we can identify where the problem will be. Regarding the status, we have the status that can be passed from the analog input block to the PID block, from the PID block to the AO block, and also through feedback for improvement. The formation of the status is a byte consisting of 2 quality bits, 4 bits of substatus, and 2 bits of limits. So there are 4 quality statuses. 0 indicates bad, 1 cert, 2 the good in the cap, and the 3 a good cap to wear. The good in the cap is where there is the possibility of having some alarm associated, some limit. The good cap, the value. It's normal without any alarm, without any associated limit. There are also the 4 quality statuses that we just discussed, and there are a total of 16 substatuses for every status. So the bad, there is a bad status, and there are 16 substatuses. They are going to inform us about what is not working well in our communication. As we mentioned, we have the substatuses there. The substatus contributes to the information of the status. There are limits too, where we have some kind of limit related to the signal. For example, 0 is unlimited, cap, lower or inferior or upper limit, or the value is constant. Here we have an example in a status byte. Therefore, we have the code 11, which signifies a good cap. The number 3 in decimal form, as we noted previously. 011 indicates an active failsafe and the set value in decimal. 00, for instance, is unlimited with no limits. 0 in decimal. So, an example of how this status appears on the network. There is a table for status codes. We need to consult this table with its priorities. Here's an example of a table for statuses and substatuses. Status good. We have the linked substatuses needed for corresponding items. They provide explanations for whether the condition is favorable or unfavorable. Therefore, it is also possible to separate into categories based on importance, ranking, or urgency, with high priority or low priority. Here we have an example of a basic control strategy, where there is an analog input, PID control. Our analog output will control the valve. Thus, when a sensor fails, it serves as an illustration of utilizing the status. The analog input block will send a bad and a substatus for sensor failure. Automatically, the PID block will initialize in IFS, which is fail-safe initialization. With that, the PID sends a status and substatus to the AO. This device may serve as a positioner but always ensure accuracy. The opening will be set to 50%, approximately 71 characters. Therefore, within the Foundation feedback system, it is possible to establish safety conditions and program status, effectively combining them. About the installation, we mentioned earlier the max distance of 1,900 meters for a Type A cable, which is a cable with electrical characteristics that we will discuss later. Just to better understand, this length of 1,900 meters is for the trunk. Here's the trunk and the total of all branches. Okay? Then we will have the total of the trunk and all the branches, 1,900 meters. Stay alert. This is the electrical representation of our network. So we have the initial terminator, the final terminator, the distance we talked about earlier, all the equipment in parallel, okay? The circuit comprises an isolator, power supply, and other components. Show the network electrically in this format. Again, here's the representation of the balanced foundation feedback transmission line, where we find a power supply circuit with the signal isolator circuit. The terminator has a 100 ohm resistor and a 1 microfarad capacitor. Finally, plus one terminator, and the distance of the field equipment not exceeding the maximum limit of 1,800 meters. How can we set up this network? A key question, right? We have several topologies. One of the frequently used topologies. This is the topology we are presenting here. It showcases the primary trunk and a junction box where we distribute close to our application the field equipment. This is an example of an installation topology. Another component of the foundation feedback network is the LES, called Link Active Scheduling. Link Active Scheduling is the one managing network communication foundation feedback. Usually, it's the CPU that does this, the main CPU. However, a field device can also be utilized in the event that the CPU malfunctions. A field device has the capability to assume control of this LES function. Another key component of a foundation feedback network is the VCR, which stands for Virtual Communication Relay Chip. It's software that serves as a communication channel. This text is used to transfer data between devices. It contains 36 characters. If a block has to send information to a different block on a separate device, ensuring minimal alteration, we will have a channel. Instead of a physical wired channel, we will have a software channel. The protocol defines 3 types of VCRs: the publisher-subscriber, client-server, and source link, for monitoring alarms and analyzing trends. Thus, the VCR includes the emitter, subscriber or publisher-subscriber, which is used for sending control data and external links. For example, sending APV to a PID and to the operation station, for instance. The client server is used for operator messages, potential changes like adjusting a set point or switching modes, tuning changes, uploading and downloading information, managing alarms, notifications, and more. And the distribution of reports through report distribution was previously used for alerting existing alarms, for instance. In the user layer, Foundation Fieldbus will have these elements. The use of functional blocks. The functional blocks will be responsible for programming the control strategy. In the function block language, Foundation Fieldbus, we can see different types of blocks. Standard function blocks, additional function blocks, which we call end-change, manufacturer-specific function blocks, the advanced ones, for example, and flexible function blocks, the FFBs, flexible function blocks. The functional block model and algorithm of function blocks. It will include the inputs, the processing of the block strategy, the outputs, which are the results, and the parameters will be configured. For example, the PID, we will have automatic and manual, the PID tuning, KP, TR, etc. So this is the generic model of a functional block. Here we have an example of block interconnection, which is the configuration of the control strategy. Here are the transmitters. A logic receiver consists of an input block for a transmitter in this scenario. The input block's output in the logic will be sent through a link to the PID's in. The PID will perform its control algorithm and send the final result to the block's output. The block's out will connect to the in of the output block in the logic. This will facilitate the operation of the Foundation's field equipment, including a positioner, act on the control valve, guaranteeing optimal performance of the control system. We can have, using functional units, length, various control strategies in the system. For example, a simple PID control. We can also develop a more sophisticated form of control, like cascade control, which is more advanced, with two PIDs. The relationship control. We have the capability to implement more sophisticated controls, such as the control of a 3-element boiler system. The Foundation Fieldbus system enables block configuration within the transmitter itself. The transmitter has a series of available blocks. In order to distribute technology, it is necessary to provide equipment. We are providing some examples of different blocks. The options at our disposal include control strategy configuration and intelligence distribution, which are readily accessible. Process control. A key component of our Foundation Fieldbus network is the host. The host is a computer that has software to establish the operations of any producer on the market. With this tool, we can easily configure the entire control strategy for effective execution, ensuring a streamlined approach. This sets us apart in a Foundation Fieldbus network. For communication between our field system and the controller, Foundation Fieldbus, and the operating system, we utilize OPC technology, which makes this communication much easier. OPC means OLE, for process control.